Hey everybody, I'd like to introduce Russell Hewett from Virginia Tech, and he's an expert in subsurface geology, and he'll be telling us about how you use computational tools to figure out, well, what's underground without actually being able to see it. Yeah, welcome, Russell.
Hi, thanks, Greg, and thanks for the invitation for the talk. So I'm going to talk today about some modeling problems in subsurface geophysics, and I'm going to lean on my background, which is largely in mathematics and computation of mathematics, to lead the discussion. Let's see, sorry. There we go. So first, I figured I would give a little bit of background on myself in modeling and how I kind of ended up working on these problems. So I started off working in solar physics, actually, almost 20 years ago, actually a little over 20 years ago, working on satellite hardware. I found that hardware engineering was not my thing. And so I switched to doing some data analysis on some of the satellites that I actually did work on, and eventually stumbled into working on a PhD where I learned about inverse modeling and inverse problems. There I worked on 3D inversion problems in the solar atmosphere. So in the context of useful things for space weather, with very large computational demands and extremely sparse data type challenges for these problems. And on the side of that, I worked on, with a large number of people, a solar data analysis package in Python. After spending about a decade in solar physics problems, I took a 90-degree pivot and started working on problems in geophysics. Again, largely from the mathematics and the computational perspective. I was interested in looking at a lot of aspects of seismic inversion, which is what the bulk of this talk will be about. But as part of this research, I worked on all aspects of it, from the forward problem, looking at new solvers for differential equations, looking at parallelism in those contexts, looking at optimization techniques and ways that physics can be used to construct partial Hessians, for example, to accelerate optimization, uncertainty quantification, ML stuff. And I also worked on software and high performance software in these contexts. And this was both part of academic work and working in industry on this problem. And since I left industry, I have kind of reverted back to a bit of a broader picture than just looking at the subsurface. But the subsurface is still a very informative domain for me. And I'm interested in all manner of physics-driven inverse problems. And I can even extend that into talking about prior-driven problems in a moment. But I'm interested in how these physics-based problems unify with deep learning and neural network type approaches, both at the mathematical and like the physical level, but also at the computation and the software framework and interacting with computers type level. And then I'm interested in extending these ideas to domains where the physics is not so physics, quote unquote, is not so easy to pose. It's more just, you can think of it as a prior, like in economics, where there absolutely is prior knowledge, but it's encoded in gut feeling of economists, or in some ecological modeling problems, where we absolutely could describe the physics that connects the chemistry of a lake or a stream to algal growth or something like that. But that physical connection is not as easily characterized by something like a differential equation. So this is, hopefully this gives you a little bit of my background here and my approach to these problems. But I'm not here to talk about any of these things. I'm here to talk about subsurface modeling. And so I want to introduce, I'm going to take about 10, 15 minutes just to broadly introduce this concept, because there's a lot of different space to explore problems in this domain. And then I'm going to dive into one specific context, because it provides some illumination, at least looking at the mathematics and the formulation of mathematics, provides some illumination about what we do when we solve this problem physically, and then also some connections to what we can do and explore in the future. So I'm going to start off with a couple of different scales of our problem. So when we talk about seismic modeling, we could be talking about it at the global scale. And so this is looking at essentially the whole Earth planetary seismology, where waves traveling through the subsurface interact with the mantle and the core, and and so on. And we can observe indirectly how these interactions behave, and then use those properties to invert for the structure of the subsurface. And this work is largely, for the most part, government funded, mostly for science, looking at plate tectonics, earthquakes, core mantle structure, this sort of thing. But there's also utility of the concepts behind this. I'll step off of Earth for a moment and talk about the sun. For a couple of decades now, solar physicists have been using helioseismology to create images of what the far side of the sun looks like. Normally, the Earth can only look at the near side of the sun, but looking at active region or sunspot structure and observing waves in the plasma on the sun's surface, helioseismologists can recover something of the structure inside the sun and also project that back outward to come up with a guess at what the far side of the sun looks like at the current time. And then quite recently, and we're hoping these results should come out. I think there's supposed to be a talk on it in a couple of weeks. Very much looking forward to this. But we've started doing seismology on other planets. We've had seismometers on the moon for a while, but InSight launched with a seismometer, single seismometer for Mars. And so it's going to be very, very interesting what conclusions Mars scientists can draw from essentially a single seismic instrument. And you'll see we're going to be talking about thousands of seismic instruments. So this is obviously a very, very highly limited, sparse data case, but it's going to be very interesting to see what conclusions can be drawn from this. Stepping back down now, we can look at data at the continental scale. So this is on the order of thousands of kilometers instead of tens of thousands of kilometers. Again, this is for mostly government-funded science applications, looking at earthquakes, forecasting them, forecasting hazards, examining the structure of the crust and the mantle. But this is typically looked at the scale of basically continents or regions, so within a whole statewide, countrywide, continent-wide. Then we get into the area that I'm I have a little more expertise in, which is at the exploration scale. This is a much smaller scale, on the order of tens to hundreds of kilometers. This work at this scale is often both government and industry funded. Again, the science applications are this kind of the same as before, looking at earthquake forecasting, hazard forecasting, understanding microseismic events, and then also doing things like monitoring and managing aquifers. On the industrial side, the by far the largest user of these techniques is hydrocarbon exploration and production. It is oil and gas production. But then also there's a lot of very recent, in the last 5 to 10 years, interest in carbon sequestration and carbon reservoir monitoring. So these applications are industrial, very similar though to some of the more pure science or government management type based applications. So that's kind of a context of why we do seismic modeling. Now I can take a few minutes and actually get us into what are the aspects of seismic modeling that we care about. So the first thing we're always going to have is some sort of data, right? And data in our case comes from sound waves that are recorded as they reverberate through the earth. And just like if you throw a rock in a pond, that sound wave has some sort of a source. So I'm going to use a star to represent that source. And of course, we don't have the ability to read the state of this wave across the entire Earth's surface. So we record that at different points, and I'll call that a receiver. And so I'm going to represent those by these upside down triangles. And when we look at these, so basically a source induces a signal that is going to be recorded by this receiver. And the recording from this receiver is going to be a time series or a number of time series that are oscillatory waves. And there are some things that in particular that we can make use of from these waves to perform inverse modeling, mapping data back to a model of the subsurface. And One of those could be the travel time of a particular event. So I have that large event on the left side there. If I know how long with the time between when that event was induced by the source and how long it takes to get to the receiver, or an array of receivers, basically, that time is influenced by the structure of the subsurface. And we can use just the travel time itself to get a coarse reconstruction of the subsurface. We can also look at the amplitude response and understand how the amplitude of the wave is impacted by the structure of the subsurface that it has to pass through, and similarly also the frequency response of the data. And then lastly, and I'm not going to talk much about this, but within these, you can also extract different information about the waves themselves, whether they're primary or secondary waves, or pressure or shear waves, P or S waves, whether they're converted waves, whether they're surface waves. All these sorts of things inform you differently about the physics and can be used differently to construct new models. So when we talk about sources, largely I can break them into two categories. We have non-anthropogenic sources and anthropogenic sources. Non-anthropogenic sources are almost exclusively going to be earthquakes. The Earth is quite seismically active, even at really, really low magnitude. But for large magnitude earthquakes, they can reverberate through the entire Earth multiple times, and the largest ones can even change Earth's orbit a little bit. That's the DC component, by the way. Anthropogenic sources are a little more varied. In exploration, you can use explosives, so literally dynamite, air guns, which are devices that are used to induce sources in the marine environment. Basically, they create large bubbles that are designed to collapse in a certain way that produce a certain signal. Vibrators, large trucks that with large vibrating cylinders that bash against the ground to induce a pattern, not unlike the dune from 1980s. But also things like nuclear testing, and then there's also passive sources, automobile traffic, other human activity, just general background noise can be used as well as a source. And then we record this with some variety of receivers. So an accelerometer-based tool on the ground would be a geophone. We could also do that with a hydrophone. And then more recently, using fiber optics, something known as distributed acoustic sensors allows you to have basically use fiber as a receiver instead of having to have a discrete accelerometer placed along a cable or something like that. These receivers are placed depending on the purpose of the survey or the study that's being performed. For a global scale, we have global observation networks, and these are maintained largely by educational and government institutions. So this is the Global Seismic Network, I think as of 2009, that includes all of the IRIS and USGS stations, as well as a bunch of affiliate stations throughout the world. And these are the networks that are largely informing planetary scale seismology. The US array is actually a sequence of data over time as this array gets moved across these columns across the states. So I think this is done according to this figure here. But this would be a regional observation network, lets you get much higher density, say within the United States, than you have from this global network here. And then at the exploration scale, you have a whole variety of options. You could have fixed arrays like you do in this case, or you could have mobile arrays like it's illustrated in this cartoon of a wide azimuth marine survey. So what you're seeing in this is there's 4 boats. Each of those boats has a little red dot after it. That's essentially the source off of those boats. So they're using multiple sources. And then you see all these long cables that are being towed. Those lines represent arrays of hydrophones that can be upwards of 10 kilometers long and contain 10,000 sensors per cable. So you're obviously getting a significant volume of data. And these seismic acquisition vessels, I think, are considered to be the largest man-made moving object when they're fully deployed in a survey situation.
Question about this.
Yeah.
What's the value of mobile versus fixed? Because I imagine the subsurface doesn't change very much. So once you have a measurement, how long do you even need to before the next measurement is useful?
So if you're thinking, I think you're kind of coming at that from a monitoring perspective, and if you're not doing anything and your assumption is the subsurface is fixed, what you're doing by having a mobile survey like this is changing essentially the angle of incidence in between reflections and the subsurface, and then the angle between the reflection and the receiver as well. And so it becomes like a computed tomography problem where you need to have 380 degrees of line of sight through the object that you're trying to image. Well, obviously, we're not going to get 180 degrees from this, but you can significantly increase the azimuth of the survey by moving things around. With the fixed surveys here, largely you're relying on earthquakes, which are distributed differently. So you're getting that azimuth, hopefully, by having a good distribution of earthquakes. But here you're controlling the structure itself.
Okay, so the value is the different angles here,
Yes.
not the same. It's never the same measurement twice, even for fixed ones.
Correct. It's not the same measurement twice.
Mm-hmm.
Though sometimes it can be, and that's used just to increase signal to noise. Okay, and then similarly for monitoring surveys, so this is a figure I pulled from a paper on an aquifer model, monitoring an aquifer in California, I think. So there's fixed ground stations given by the triangles, and then there's monitoring wells given by the circles, and yeah, so these again are kind of more fixed in place. They could be structured because you could set them up just like you would for a land-based exploration seismic survey if you want, or something that's a little bit more randomly distributed, like this one here, which is likely leaning on an existing network of receivers. Okay, so now the question is, how can we recover the subsurface from these seismic observations? So our data are going to be things that look like this gray thing on the left, which is basically this is a picture of a single source, and the results horizontally are going to be data recorded by different receivers along a component of the subsurface, or actually they're along the surface. We don't have them in the subsurface, though we can. And then I want to recover, the subsurface model, say this cartoon model that we often use in seismic is just a really quick testing problem. And so if you're not familiar with inverse problems, just establishing terminology, when I'm talking about a forward problem, I'm given the thing on the right, some sort of model realization, and then I want to pump it through a forward solver, which is often quite related to physics, so maybe a PDE solver or something like that. And that gives me a realization of a potential sample data, which then can be used for analysis and inform and update. If we take this workflow and kind of rotate all of the boxes by 2 slots, we'll end up with what looks like more like the inverse problem workflow. So given some data realization and maybe some other priors, we can pump that through an inverse solver to come up with potential model realizations, as well as maybe posterior statistics on those models, which can then be applied for inference and analysis, which updates our prior or then goes on to do something else. So this is the context that I'm thinking about here. We have to solve a lot of forward problems in order to solve inverse problems usually. But really, it's this mapping from data to model that's of interest. There are other modalities, imaging modalities used in subsurface recovery. So controlled source electromagnetism, gravity, LiDAR, and there's others. I'm going to restrict my discussion to seismic, just keep things simple here. So there are 3 modalities within seismic that I'm going to talk about. The first is seismic tomography. And so this is what I was talking about where we were interested in the travel times. So here our input is observed travel times or ambient noise. And so the observation of those travel times comes from the seismic data, and the events of interest and their times have to be either hand-picked or machine-picked or in a semi-supervised way is the way it's usually done. Though fully unsupervised approach would of course be ideal. And so given that forward travel time, not from a single source to a single receiver, but from multiple sources to multiple receivers, we can pose all of that through the forward model of a travel time integral equation and invert that for essentially the amplitude map back to the velocity. And this produces a smooth subsurface velocity. It is iterative, so we have to start from some initial subsurface model. So that might be a 1D model, like the one that I have there for B initial on the very bottom. It's a 2D subsurface, but we just assume we have one vertical profile that's the same everywhere. Might come from community models. This data is very sparse and it's very computationally intensive. So within the scientific community, they will put together global models and regional models that other researchers can use as a starting point for their algorithms, so you don't have to bootstrap everything from scratch. And then similarly, prior inversions. And the objective here is to fit the travel times to recover a velocity. This can only get you something smooth. Full waveform inversion or seismic inversion, which is what I'm mostly talking about today, the input is the same observed seismic waves, except we don't do anything to them in an ideal case. Obviously, there's a lot of processing that happens. Our forward model is the wave equation, whether we want to pose it in the time and frequency domain. The Earth is generally elastic, so we would ideally use elastic physics, but often it's approximated with acoustic physics or even a joint acoustic elastic posing. And then we start maybe with this subsurface, this smooth model as an input or community model or prior inversion, and then can recover the velocities and densities and things like that as part of the fitting of the seismic waves. So I've got some synthetic data here on the right. The top is a function of time in the y-axis, and then the x-axis, which is labeled the y direction because this is x, y, z. So this is a fixed x. So a single line of receivers in the x direction, whereas the one on the bottom, I have fixed time, and I'm looking at the data spatially. So this is the plan view of that. So this was a 3D experiment that I did. And then just a 2D recovery here, just to give you an idea. So I start with maybe something smooth like in the middle, and after a number of iterations, I can recover something that looks like the thing on the bottom, which is close, except in areas where I have very low coverage with signal, like over in the bottom right and left-hand corner. And Greg, this kind of goes to your question of why you move things around. If I could have put sensors off my screen, I would have a better job I'd be able to recover those areas a little bit better in my initial model, and then therefore maybe recover them better in the inverted model as well.
Actually, on that one, is there a notion of where should I put my sensor in order to reduce error at best?
Yes and no. Yes, if you know something about what you're imaging, which is difficult. But there is optimal design, but that's iterative as well. And I'll talk a little bit about that a little bit later on in the context of some of the business discussion.
Got it. Thanks.
And then the last is seismic imaging, which so you have to be careful when talking about, particularly to like an inverse problems person in seismic context. Inversion is the recovery of the model parameter itself. Imaging is usually the recovery of some derivative product of that. And usually that's going to be maybe like a reflectivity model. So you can think of this as kind of linearizing the other problem or using an edge detector on the other problem. So forward model here is a linearized wave equation. And here we want to fit perturbations of the observed seismic waves. And this gives us a model of the reflectivity, but not necessarily anything about the specific material properties. Why would we use all these different modalities? Well, so I've gratuitously taken this figure from a few people. We find that as a function of the input frequency, there are different regimes where seismic data responds better. So low frequency is much more responsive to velocity, high frequency is much more responsive to reflectivity. And this kind of intermediate range of 3 to 10 hertz is actually rather insensitive. Well, this low frequency regime corresponds to tomography, high frequency regime corresponds to migration or imaging, and inversion is really what we hope to use to kind of cross that bridge. So without loss, or with minimal loss of generality, I'm going to focus on full waveform inversion. I'm going to stick to the exploration context here for the remainder of the talk. So this great beast of a thing is my complete or pedantic version of a full waveform inversion objective, which I'll talk about a little later. But for now, I want to stay with this idealized picture, which is largely just a data misfit function. And most of the time we pose this in terms of just a nonlinear least squares problem. D is my data, M is my set of physical parameters that I'm trying to recover, and F is my forward modeling operator or my solution operator for that. To pose this a little bit more completely, we can look at this as a PDE constrained or partial differential equation constrained optimization problem. So I have my nonlinear least squares problem constrained such that the solution satisfies some differential equation and that f is my solution operator for that differential equation. The physical prior, again, I said it's going to come through a PDE, and we can impose this in the time domain with the wave equation, in the frequency domain with the Helmholtz equation, Laplace or Fourier domain, whatever you want to pick. There's different benefits to and drawbacks to each of these. There's definitely no free lunch in this area. So I want to show an example of this. So let's consider a very toy problem, second order isotropic acoustics under a constant density assumption. And I'm going to have some velocity. And so this is the setup of the problem here. Actually, sorry, we'll get to the setup in a moment. I have my forward model. And so in this case, it's just going to be the second order isotropic acoustic wave equation, which is on the right-hand side. I can take that same thing and I can linearize it or use Born modeling and come up with the linearized version of the wave equation. You'll notice that the operator here doesn't change, but this maps perturbations in the model to perturbations in my data. And then I could, from here, I can derive the adjoint model, which would often be called the backward model, but it's very important to refer to it correctly because while this equation can be run backward in time, in general, that is not always an assumption that we have. So be more specific, it's the adjoint model, which yields our mechanism for computing the gradient, which is essentially just the correlation between the second time derivative of the incident field, the thing that comes from the first model, and the adjoint field, the thing that comes from the adjoint modeling step, which takes a residual as an input, essentially mapping perturbations in data back to perturbations in models. All right.
So question about just basic methodology. How different is this from automatic differentiation in terms of the algorithm? Or is it just like you do it?
I'm going to talk about that actually, but the answer is it is not all that different. So automatic differentiation is a mechanism to get to induce the adjoint state method and to compute the values that the adjoint state method would yield. So backprop is an adjoint state method, and I'll talk about that at the very end of the talk here. But one of the main differences from this and what we'll see here, though, is that here my adjoint PDE actually has physical meaning. In the context of a neural network, the adjoint operator doesn't always have an intuitive meaning here. But we can actually see some physical intuition from this, which is what I'll show you in the next in a video in a moment. So to set up this demo, I'm going to work. Yeah, go ahead.
Can I think of it as the chain rule?
So yes, and that's the same way you would think about it in terms of a neural network, right? But here it's a mathematically same idea, but physically a little bit, I said a little bit more concrete than that. So here's the setup.
I have a question.
Sorry, I can't see any cameras. So
is the agent system like a forward and agent system are self-agent?
In this case, they're self-adjoint.
Okay, cool.
But in general, that is not a valid assumption.
I see.
So this is just a toy problem that's simple enough to write on one slide. And this is expressing essentially that the adjoint in this case is expressing the time reversibility of this particular wave equation.
Yeah. Okay. Thank you.
All right, so let's look at a movie of this in a second. So I've got a very, very simple problem here. Constant velocity of 1. It's a 1D problem, except for this perturbation that is about halfway through my domain. I'm going to have a single source and a single receiver. Source is at 0.1 and the receiver is at 0.25 in my domain. And I'm going to show a movie of a couple of sequences of movies that build up the steps that the inversion process is going to perform, starting here. And you'll see a space-time diagram. So I'm going to show the picture of it first so that you see what you're seeing as this assembles. But this is the solution field as a function of time and space simultaneously. So what you're seeing is the source injection here at the bottom left-hand corner and data propagating through the domain. And then I have absorbing boundary conditions that are not quite perfect. So you may see some further reflections off of the boundaries as time goes on. So I'm going to show some movies now of this, and then the next few steps in the process, and then we'll look at just the resulting images again, just to kind of make that a little more concrete. So here's the first one. So this is on the bottom left, you're going to see the instantaneous wave field at the current time, and then the source function as it evolves, as that's being injected into the problem in the top right, and the data that's being recorded in the bottom right, along with the evolution of the space-time diagram. So we can see right now we're going to hit the reflector. Some is going to transmit through, and some is going to reflect back to the domain. And then now we're just getting numerical imperfections reflecting back around inside my problem. And we see that with the data on the bottom right. We get that big initial recording as the direct wave hits the sensor from the source. And then that next big blob here is going to be the reflection back through the receiver. So this would be my true data, right? This is the data I would observe if I inject this source through this receiver in the true medium. Now, if I don't know that the medium has this big reflector at 0.5, we want to try to recover what that looks like. So on the left-hand side, you'll see the same thing as we saw in the previous movie. And then on the right-hand side is going to be what I'm going to show is the incident field. So this is just assuming a constant velocity of 1, no reflector in the middle of it. And in the bottom right, I'm going to show the difference of the data recorded, say, on the one on the left side versus the one on the right side. Because that residual is what we're going to back propagate through the adjoint wave equation here. So you'll notice the direct wave is exactly the same. So even though we've recorded that direct wave, that first big impulse on the left side, it doesn't show up in the residual. But because we don't have the reflector, every part of that initial forward data that is due to that reflection appears in my residual. So that contains all the information about the reflector, or at least some information about the reflector that we can use to try to reconstruct it. So that bottom thing, the bottom right-hand thing is going to be our input for our adjoint problem. And then I'm also going to need the incident field, the entire incident field, in order to reconstruct the perturbation. Because remember, we have this correlation between the adjoint field and the second time derivative of the incident field here. So let's go to this last video. So this is the adjoint problem. So now we're starting at the end. If time moves forward, the adjoint of time moving forward is time moving backwards. So we're going to integrate backwards. And then on the upper right-hand side, you're going to see that adjoint field evolve as we inject the receiver data, the residual at the receiver location. So in the forward problem, we have sources and receivers. And in the adjoint problem, our receivers actually become the location of our sources. And the residual waves are basically back propagated and reflect about in that initial medium that we had. Bottom left, you'll see this is the adjoint source being injected. And then in the bottom right, I'm going to show as a function of time, the assembly of the perturbed model here. So we move back in time. Not a whole lot happens. We start to encounter residual due to the numerical imperfections. Not a whole lot's happening. And then, boom, we hit the main source. And very quickly, that main component of the residual intersects at a point in space and time with that incident wave. And that actually happens to be at 0.5, which is where our known perturbation is. You'll also see other small perturbations here. And I'll have a bigger picture of this back in my slides in a moment. But you'll see small perturbations off to the side. Whoops, and I killed my video here. Those are due to the interaction of these spurious reflections, essentially producing ghosts of the reflector at different depths in my problem. All right, so let's take a quick back look at this again without the video to hopefully make it a little bit easier to see. So this is the interaction between the incident field and the adjoint field. And because they're roughly the same color scale, this is hard to see. But everywhere that these interact, you're going to induce a component of reflection. And so to exaggerate this, I way thresholded and colored these things. And so anywhere that you're seeing yellow here is the incident, and blue is the adjoint, and then green is the intersection of them. And you see that the bulk of this is occurring right around that reflector at 0.5. And then you'll see further spurious interference, constructive interference that's happening due to other reflections off of boundaries and things like that. And so the blue thing here is the model that we recover, or the perturbation that we recover anyway. And the black thing is the true perturbation. This perturbation, delta M, is a gradient. We would pump that into a gradient-based optimization scheme, run this hundreds of times for, hopefully in a 3D environment, hundreds of thousands of sources, and create enough of an update to a gradient to update our model sum. So why do we care about adjoint states? It's largely a cost-driven thing. So if this is my forward model, my forward modeling costs 1 PDE solve. My linear forward model, if I needed it directly, would cost me 2 PDE solves for using an adjoint state method. But if we wanted to try to form this linear operator F, that's nearly impossible. So for just a really quick illustration, it's just some matrix, which we could induce by hitting that matrix against, via these wave equations, hitting that matrix against the standard basis. So if I have a 3D survey, the M, the number of rows in my matrix, is driven by the number of samples. So a very small survey, 10 lines, 1,000 receivers per line, with a short recording, so 8 seconds per recording and 8 millisecond sampling, which is quite long. So normally recordings would be about twice that. The sampling would be down to 2 milliseconds, but this is 10 million samples. And then if I have to check out the response to every voxel in my simulation, so this simulation would be, say, on 1/8 of a large benchmark model that we use. So that's 657 million degrees of freedom, which would yield a matrix that takes almost 24 petabytes to store. And if we had to compute it for a single source, if we could solve 100,000 wave equations a day, it would take us 18 years.
Question.
Yeah.
What's the numerical software you use to solve this PDE?
This was just a simple leapfrog finite difference scheme.
Finite difference.
We use a lot more than you'd use finite differences, discontinuous Galerkin methods, a whole variety of different things. But this was just a toy. And then,
I have a question. When you construct the adjoint source, do you have any difficulties balance different frequency components?
So, if I understand what you're asking, do you want to filter the adjoint source in some way?
Yeah, filter the source in some way so that I don't know what's the objective function you use, but
it's just in this case it's just a least squares, just a direct.
But is there any is the function of the frequencies? So
there's some aspect of it, and I have a figure about that in just a moment, actually. So my forward modeling is 2 solves, and then I can do my adjoint modeling with essentially 2 plus solves, basically. So 2 versus 108,000 times 100,000 times 18 years. Obviously, adjoint state method is going to be preferred here because they make this optimization feasible. So it means I can evaluate my objective at the cost of 1. I can evaluate my gradients with a cost of roughly 2. And if I wanted to, I could even evaluate the action of the second derivative matrix, the Hessian, at a cost of roughly 4 times the cost of evaluating the main objective. So we can do toy inversion starting from this 1D problem in the middle. I can recover this. This was with an experimental solver, which is why it's so tiny. So it's not a realistic result at all. But for realistic results, we don't actually use, the interpreters don't actually want to see the inverted material parameters. They want to see seismic images. They want to see the reflectivity maps. And these are found by applying migration algorithms at much higher frequencies to the material parameters that you recover. This migration procedure is essentially backpropagation. You could think of it as a gradient calculation in FWI. So for example, I said for this other equation, my gradient is the correlation between the adjoint field and the second derivative of the incident field. Well, what's a couple of derivatives between friends? The correlation between the adjoint field and the incident field itself is going to be close enough in a lot of ways. And it actually takes some the additional wiggles that the second derivative would induce out of the picture, and hopefully provides a little bit more accurate reflectivity map.
So is that the idea? Just to understand, I get the right frame.
Yeah.
You were solving for the propagation of the wave? And you just simply, once you solve for that, you just run that wave, well, it gets backwards in this case, to figure out what the subsurface must have been.
Yep.
Is that how, okay.
To figure out a perturbation of it. It's exactly a transpose in least squares problem.
Okay.
It's just the problem is that we pose everything through the PDE constraint, and that induces an adjoint differential equation that tells us how to get to this gradient calculation.
Got it.
And so when you have that, you can produce a reflectivity map like one that we looked at before. Now, real-world results at like reservoir or exploration scale are hard to come by. They're worth a lot of money, so companies don't publish them. There's a really nice one in this paper, though, that CGG released. So this is an initial velocity model. That's the color map. So blue is like 1,600 meters per second. Red is, I think, like 2,200. So this is a relatively slow depth. This is plan view. So you're looking at a single depth slice. And then the background variation is actually a seismic image based on one of these models that's overlaid behind it to help establish some visual structure. After full waveform inversion, this is the model that they come up with. So you can see some areas go slower to faster, some go faster to slower. And you can take this and produce a seismic image from that. This yellow circle is just they're missing a line in the data, so they're highlighting the effect of that here. And then this last picture here shows you areas that got slower or went faster. So areas that were red went faster, areas that are blue became slower. And you're seeing river channels and things like that in the subsurface here. So these, it's very nice that they publish this and make it available to show, because otherwise this stuff is very, very hard to come by publicly. So I have about, I think, 5 to 8 minutes. So I want to move a little bit quickly through the remainder of this just to get some of these ideas in, and then I'm happy to talk a little bit more about it. There are a lot of challenges working in full waveform inversion. And so one of them is this notion of cycle skipping. And this is just induced by the physics. If you're trying to fit oscillatory things to oscillatory things, there's going to be a lot of local minima, right? So this causes the optimization problem to be it's locally convex, but highly non-convex. My example is always, if you're used to image registration, we have similar techniques to solve it. But if I want to register my hand, which you probably can't see because I have the screen sharing, but you can imagine if you're moving one hand across the other, you have 9 local minima in that registration, even though there's going to be 1 global maximum. That's that cycle skipping problem. If instead of solving the problem using time domain physics, we use frequency domain physics, we can get around this a little bit by solving the problem at extremely low frequencies, fitting my low frequency hand, and then taking that updated velocity model and trying to fit higher and higher frequencies. So this gets to the idea of the question of maybe applying frequency filters. But here, you're not just frequency filtering the data, though you could do that. You're actually frequency filtering the entire optimization problem. And this is known as frequency continuation. And there are some theory that shows that this is optimal. This is similar to ideas of Gaussian pyramids and registration, and almost any other like multi-scale type algorithm where you fit primal things at low frequencies and then just only update essentially what amounts to error at higher frequencies.
Actually, a question. I didn't understand cycle skipping, and that seems like a pretty important point.
Yeah, so if you look at this picture on the left, take the black signal as the background, or as the true signal, and then if I have this signal that's up at the top in the dotted line where it is, you can shift it back or forward by half a period, and it would have the same energy. The misfit would have the same energy. It would be an exact fit, right? So
yeah, that helps then.
Yeah, so this idea is that if you have an incorrect velocity component, it can still induce a good fit in the data because it's all oscillatory. And so you'll actually amplify the fact that you're incorrect, and that's a local minimum in the optimization. So as I said, you solve this with Helmholtz instead. This example was actually done using the frequency continuation idea. It's also very expensive. The Earth is neither acoustic nor constant density, so all my assumptions in that little toy are completely garbage. More realistic physics requires a lot more computational power and more and better data. So single component data is not good enough anymore. We have to be able to accurately address the coupling between the acoustic ocean and the elastic Earth. And this drives incredible computational cost because if you're familiar with solving wave PDEs, you have stability conditions, and stability condition requires that very, very, very small time steps when we have very slow velocities. And the shear wave velocity for elastic problems right near the surface is the absolute slowest. And so you can get just orders of magnitude in computational cost just by trying to couple acoustic and elastic domains together. So if we wanted to solve this with full-blown elasticity, we'd be looking at over hundreds of times the cost of the little toy that I showed, having 81 material parameters and 9 overall solutions. Obviously, under a number of symmetries that are very common to use, we could reduce the number of parameters, because who wants to look at 81 of them? But even then, we're still talking significant computational cost. And so we get more compute to do that better. But then having more compute, I've never heard a geophysicist say, I want lower resolution or I want worse physics. So you establish a boundary and you're always pushing it to get better and better and better physics here. I've also simplified the objective function for academic purposes. So as I said, misfit of data. Realistically, this is not just one piece of data. This is data from tens of thousands of sources. So we have to sum over all of this. And then we have a whole arbitrary amount of filtering and restriction and regularization that we would have to apply as well. Oh, and we don't know the source function. I've idealized that I know the source function here, but if you're using something that's like an explosive in the subsurface, you have to invert for what that explosive is, because what that source impulse actually is, because it's not something that we can easily characterize mathematically. So it's a joint inversion for both the source now and the subsurface model. Yeah, I'll skip this just in the interest of time. The point is computational scale has just gotten absolutely massive. So the CM Phase 1 is a community benchmark that we use. It's a 3D benchmark it's basically gigascale velocity and elastic material parameters, provides over 60,000 sources paired with 400,000 plus traces per shot, resulting in about 200 terabytes of synthetic data that can be used as a benchmark inversion. And the reason this volume is so large is that this is the scale of which an exploration scale seismic survey would be producing data. Now, these surveys are not cheap. They cost hundreds of millions of dollars, give us hundreds of terabytes of data, which we then have to use hundreds of petaflop of compute to recover the velocities. But that's, while I'm the scientist side, that's the inverse problem. That's where I'm interested in. That's the modeling. But these FWI models are only part of a sequence of tasks. They're a user of geological models, and then they become inputs to reservoir models that are used to monitor capacity or forecast production or evaluate the safety of operating in an environment. And then to decide, to go back to Greg's question, we actually don't have enough resolution in a certain area and we need to de-risk the operation more. So you go back and you shoot a whole nother survey at a cost of another $10 to $100 million. But the whole point of this is to be able to evaluate whether or not it's economical to do business there, whether it's economical to produce oil and gas or to sink carbon or whatever in that environment. So these are all inputs into economic models. So then the question that we might ask, and we've talked about this a little bit in the talk, is, where does machine learning fit in? Well, I've talked about just taking data directly to model with FWI. And of course, there's what if we just put an ML black box in the middle of it? We can just map data directly to models with that. And of course, people try this. Then there's also the interpretation of machine learning is a really good image processing tool. So what if I take FWI and produce models that ML can enhance and do better with? What if I can enhance my data, or I can filter my data better before I pump it into an FWI scheme to get better models? And these are again things that are kind of say first order things, operations that ML can contribute with. But where I'm interested in as a researcher is this last part, which is how do we put these two things together in a cohesive framework? And so the first thing that I've already discussed this, but we have to establish is that deep learning and adjoint state methods are mathematically and computationally related. And so backprop is basically the adjoint state method. So if you take the problem I have up at the top, this is a simple, nonlinear least squares problem where instead of f being a solution operator for the wave equation, it's the evaluation operator for the LNF5, MNIST classical neural network, and it's like 6 layers or whatever it is there. And I can take that, and I could take the same procedures that I do essentially by hand that are done by an automatic differentiation tool. I could do those by hand and produce an adjoint state, an adjoint operator sequence just like this, just like I do for the other problem. Except there, again, physics has some meaning. Here, it's not quite clear what the meaning of the adjoint of the pooling operation or whatever. But what this means is that I can pose FWI in deep learning frameworks, and that's actually what got me interested in deep learning once I made that realization 3 or 4 years ago. Second is thing that we can exploit is that ResNets are basically ordinary differential equations, and training a ResNet is an ODE constrained optimization problem. So now we understand, okay, the math plays well, both from kind of a mechanical perspective and from a theoretical perspective. And we can use this to, more generally physically constrain machine learning. So one approach people use is to use a neural network as a prior for a PDE solution. And this is what a physics-informed neural network is. It's, optimizing some distance function subject to a constraint that the neural network satisfies the differential equation at a set of co-located points in the differential equation space. Alternatively, we could use the neural network as a prior for the physical model itself, and this is a notion of a deep prior. I've done some experimenting with this again at very small scale, which will lead into my next and last content slide, which is if you take FWI, you get the thing on the upper left, and you'll notice that FWI is not very sensitive to the faster velocities in the lower depths, but a straight up deep prior is not at all sensitive to the high frequency stuff at shallow depths. But if I put the two together in a clever way, this is not just adding the two resulting images. I can get something that does a decent job of recovering both simultaneously. But this is inordinately computationally expensive, which led to a lot of what my current research is on, which is to how to put an expensive tool like deep learning together with an even more expensive tool like full waveform inversion. And so you can exploit the fact that the computational frameworks can be the same for both problems. And then to do that, then you have to exploit parallelism. And FWI, wave equations, PDEs are very naturally model parallel in a domain decomposed environment. But neural networks are not. But there are ways that you can write them so that you can more easily exploit that. And that's what a lot of my recent research is on, including working domain decomposition into PyTorch framework, which allows kind of arbitrary parallel decompositions of tensors and neural networks and things like that. And ultimately, that will all circle back around to these sorts of problems. So I think that's all I have to say with that, some credits and attributions. And then I have a few software packages I encourage you to check out. You're welcome to get in touch with me. I'm a scientific advisor for X as well. So I already have a relationship with Alphabet and that context, so I can work within things there. And there's my website as well.
Well, thank you very much, Russell. It's fantastic. Are there any final questions from anybody?
Yeah, I have a question. So for the physical simulation, it's pretty expensive. Then when you construct the neural network, are we going to simulate many times, get the data to train a model?
It's the same as with any standard neural network training. The forward pass through the differential equation has to be performed for each source function, essentially in a batch, right? So if you do mini batching, you have to do it once for each data point. In a neural network, it's going to be the same for the inversion and for the joint process. You can't reuse it.
Okay, but neural network should be like pre-trained. But my question is, how many data we need to be able to train this model in advance?
To train the neural network itself?
Yeah.
So no, I'm looking at training them jointly, so that the underlying model parameters are actually parameters of the network, not of the parameters of the network, not just necessary physical parameters.
Okay.
So the training the neural network is part of training the solving the problem itself.
I see. Okay. So the motivation of combining neural network and physical simulation, the PDE, are you going to like reduce the number of forward simulation, or what's the motivation?
So there's a couple ideas there. Is that a parameterization of the subsurface using voxels, gigavoxels, is over parameterized, and you can reduce that a little bit with neural networks. You could use them as generative structure. You can impose structure in the network itself that regularizes the result. There's a lot of different things that you can do once you have that capability.
Okay, I see.
But that's open research.
Cool. Thanks.
Well, thank you very much. This was very fantastic.